Hello everyone. In the previous lectures, in the previous videos, we have discussed the theories of bonding in complex species. There we have discussed valency bond theory and crystal field theory. To is valency bond theory and the crystal field theory, there were some merits and some demerits. Some of the properties of complex species can be explained by valency bond theory, whereas some of the properties cannot be explained by valency bond theory. Then to overcome this, again the new theory was proposed, that is crystal field theory. By use of this crystal field theory, some of the properties of complex which could not be explained by valency bond theory were explained, but still the crystal field theory was having some demerits that we have discussed in detail. Now in this lecture we are going to discuss the nature of bonding in methyl carbonyls. That means when methyl and carbon monoxide forms a complex, then what is the nature of bonding between carbon monoxide and the metal? So let's start with nature of bonding in methyl carbonyls. Bonding in methyl carbonyls. So we are having carbon monoxide as a ligand, and this carbon monoxide as a ligand forms bond with the central metal. Now whenever carbon monoxide forms bond with the central metal, the metal is always in low oxidation state. In most of the case, metal exists in zero oxidation state. So first thing that we have to keep in mind is, whenever we have complex between metal and carbon monoxide, the metal always exists in the low oxidation state, that is the zero oxidation state. Second thing, carbon monoxide, if you look at the structure of carbon monoxide, carbon as well as oxygen both has got a lone pair of electrons. So the question arises, while bonding with the central metal, whether this is the carbon that is bonding with the metal or this is the oxygen that is bonding with the metal. So now look at this, we have this carbon monoxide. If you look at this carbon monoxide, we have this carbon oxygen triple bond. Now to satisfy the valency, oxygen is having a lone pair of electron. Simultaneously, carbon is also having lone pair of electrons. So now question arises, either bonding can be through oxygen or bonding can be through carbon. Now to solve this problem, we take the help of electronegativity or the polarizability of the ions. Carbon as well as oxygen. Now look at this. Oxygen is more electronegative than carbon. When we say oxygen is more electronegative than carbon, these lone pair of electrons will be held more tightly by oxygen than by carbon. So the lone pair electron on oxygen is held more tightly because oxygen being more electronegative, whereas the lone pair electron on carbon is held less tightly by carbon because carbon is less electronegative. Now the lone pair on carbon being held less tightly by the carbon, these electron pair present on carbon can easily be donated. As the carbon is less electronegative, the lone pair electron on carbon can be more easily polarized, since Carbon is more easily polarizable than that of oxygen. Whenever metal forms a bond with carbon monoxide, this is always through carbon, not through oxygen. So look at this. Carbon is less electronegative. So carbon being less electronegative, electron pair is held less tightly, so it can be more easily donated. That means carbon being less electronegative, the lone pair electron can be more easily polarized. Hence, in metal carbonyls, the bonding is through carbon only. Bonding is through carbon only. So, in metal carbonyls, the bond formed between the ligand carbon monoxide and the metal is always through carbon. The reason is carbon being less electronegative, the electron pair on carbon is held less tightly by the carbon and can be more easily polarized. On the other hand, oxygen being more electronegative, the electron pair is held more tightly. If the electron pair is held more tightly, the polarizability of this electron pair will be less, or this electron pair can be less donated, and the bonding through oxygen is less visible. So, in metal carbonyl, bonding is always through carbon and metal. This is the reason why bonding through carbon takes place. Now, coming to how this metal carbonyl bond is formed. So, I told you in metal carbonyls, the metal is always in lower oxidation state. Lower oxidation, most of the case, zero oxidation case. In zero oxidation state. Look at this example. Iron pentacarbonyl, so iron is zero oxidation state. Ruthenium pentacarbonyl, again zero oxidation state. Osmium pentacarbonyl, again zero oxidation state. Nickel tetracarbonyl, nickel zero oxidation state. Vanadium hexacarbonyl, again zero oxidation state. So most of the case, the metal is in lower oxidation state or zero oxidation state. And if you look at this electrochemical series, this carbon monoxide is on the extreme right hand side, that is a very strong field ligand. Very strong field ligand. So we have this carbon monoxide, which is a very strong field ligand. So whenever this metal forms a bond with carbon monoxide, bonding is through carbon, because carbon is less electronegative and electron pair is n less tightly, which can be more easily polarized. Second, in metal carbonyls, metal is always in zero oxidation state or low oxidation state. Third, ligand carbon monoxide is a very strong field ligand. So whenever we have this strong field ligand, in most of the case, this ligand will force the electrons to pair up in the d orbital. Now coming to the bonding part, this carbon monoxide, if you look at this, the molecular orbital theory of this carbon monoxide, number of electrons in carbon monoxide is carbon atomic number 6, oxygen atomic number 8. So we have 14 electrons. So total number of electrons in carbon monoxide is 14 electrons. Carbon atomic number 6, oxygen 8, 8 plus 6, 14. So write this electronic configuration. We have sigma 1s, sigma star 1s, sigma 2s2, sigma star 2s2. Then we have sigma 2pz2, pi 2, 4, 6, 8, 10, pi 2px, pi 2py, 2, 4, 6, 8, 10, 12, 14. Then look at this very careful. This is D-channel level. The pi star, that is anti-bonding. These two pi star is unoccupied. So in carbon monoxide, the anti-bonding pi orbital is totally vacant. So these anti-bonding pi orbital being vacant, these orbital can also be involved in bonding with the metal. So one of the most important criteria of ligand is ligand should be having at least a pair of electron which can be donated to the central metal atom. When this ligand donates a pair of electrons to the central atom, the ligand is showing the basic character, that is Lewis base, whereas the metal atom is accepting a pair of electron. So metal will act as a Lewis acid. On the other hand, the metal in methyl carbonyl is in zero oxidation state, so we have a lots of electron in the d orbital of metal. So these electron can be further back donated to the vacant antibonding orbital of the carbon. As a result, there is a tendency for formation of big bond or pi bond. So in methyl carbonyls, ligand act as a base as well as acid. Similarly, the metals also act as an acid as well as base. So now coming to this bonding, now let's take this case. We have this metal carbon monoxide. Now metal is in lower oxidation state, so metal has got some unoccupied or the vacant d orbital. Now the vacant d orbital or the vacant hybrid orbital of the central metal atom overlaps with the filled sigma orbital of this carbon monoxide having pair of electron. So this overlapping of vacant hybrid orbital of the central metal and the sigma orbital of the carbon monoxide having pair of electron forms a sigma bond. That is, so this is a sigma bond that is formed between metal and carbon monoxide. Now this bond is formed by overlap between vacant hybrid orbital of metal with filled sigma orbital of ligand. So look at this. We have looked at this metal, and this is, we have carbon monoxide. Now look at this. This carbon monoxide has got filled sigma orbital, and this metal has got vacant hybrid orbital. This is vacant hybrid orbital. Now these sigma filled containing a pair of electron and this vacant hybrid orbital of central metal, both are in the same direction, so there is chances for overlapping between these two. When this overlaps, a sigma bond is formed between this is a sigma bond that is formed. So since both the electron is coming from the ligand, so this is dative bond or coordinate bond. So this is sigma bond that is formed. So as I told you, the sigma bond between the metal and the ligand carbon monoxide is formed by overlapping the filled sigma orbital of carbon monoxide containing a pair of electrons with the vacant hybrid orbital of the metal, forming a sigma bond. Now when this carbon monoxide forms a bond, sigma bond, with the metal is already in the lower oxidation state. Metal d orbital has got lots of electron. In addition to the electrons present in the d orbitals of the central metal, a pair of electron is also coming from the ligand. That means more and more electron is accumulating on the metal. Now when ligand transfer electron density to the metal, electron density on metal increases. So already the d electrons present in the d orbital of the central metal and the electrons coming from the ligand, there is a repulsion. Because of this repulsion, that is due to excess accumulation of electron density on the central metal, the potential energy of this system increases. As the potential energy of the system increases, the stability of the complex will decrease. So to overcome this, what is doing is, now the metal having high electron density will try to reduce its electron density. Now to reduce this electron density, the only possibilities is metal has to transfer some of this electron density towards the ligand. So for this back transferring of electron density from metal to the ligand should have some unoccupied orbitals which can accept the back donated electron density. So as I told you earlier, while we write electronic configuration of carbon monoxide, we have unoccupied antibonding orbital. So these unoccupied antibonding orbitals can accept a pair of electrons from the metal. So metal back donating electron density to the vacant antibonding orbital of carbon monoxide. Due to this back donation, electron density on this central atom will decrease. As the electron density is decreased, the stability of the complex will increase. Due to this back donation, a pi bond is formed between the metal and ligand. Due to the formation of this pi bond between metal and the carbon of carbon monoxide, the metal carbonyls are very stable. So when we say a pi bond is formed by back donation from the filled d orbital of the metal to the vacant antibonding pi orbital of carbon monoxide, the metal carbon bond becomes double bond in character. When the metal carbon bond becomes double bond in character, the bond order between carbon and oxygen will be less than 3. So as the bonding between metal carbon increases, the bond between carbon oxygen will decrease. That is, the bond strength will decrease. So this is the formation of sigma bond. In this formation of sigma bond, this ligand carbon monoxide is acting as a Lewis base because this is transferring electron density to the metal, and the metal is accepting a pair of electron, and this metal is acting as a Lewis acid. So during the formation of this sigma bond, by overlapping between the vacant hybrid orbital of metal and the filled sigma orbital of carbon, carbon monoxide is acting as a Lewis base, metal is acting as a Lewis acid. Now coming to the second part, that is the formation of pi bond. Formation of pi bond. Now for this formation, what is, as I told you, metal is having excess electron density due to the accumulation of more and more electrons coming from this ligand. And to decrease this electron density, metal will try to transfer electron density to the carbon monoxide. So in this formation of pi bond, the filled d orbital of metal will overlap with the antibonding pi orbital of the carbon monoxide. So we have look at this. Metal so this is filled d orbital of metal. So metal has got filled d orbital, plus we have carbon monoxide, that is ligand. Ligand has got vacant pi star orbitals. So the vacant pi star orbitals of ligand overlaps with filled d orbitals of the metal. This results in the formation of pi bond. So we have looked at this metal, carbon monoxide. So look at this. In this case, the metal is transferring electron density towards the ligand. So in this case, metal is acting as a Lewis base, whereas the ligand is acting as a Lewis acid. So in metal carbonyls, both ligand and metal shows acidic as well as basic behavior. Now because of this transferring of electron density from metal to ligand, we say that is metal ligand pi bond. This is pi bond. As I told you, this is formed between filled d orbital of metal and vacant antibonding pi orbital of ligand. Pi formed between filled d orbital of metal and vacant pi star of carbon monoxide. So because of this back donation, electron density on metal will increase. So at the end of the day, the electron density on metal remains unchanged. So as the electron density remains unchanged, so the potential energy will be the least. As the potential energy is the least, this will be the most stabilized. And second thing, due to the formation of this pi bond, the bond order between metal and carbon also increases. As the bond order increases, stability of the complex also increases. Due to increase in this bond order, the bond order between carbon and oxygen, which was supposed to be pure triple bond, now this is less than triple bond. So combining these two, as this formation of pi bond due to back donation of electron density from filled d orbital of metal to vacant d orbital of pi star orbital of carbon monoxide. This is known as synergic effect. So keep in mind, this is synergic effect. So synergic effect is back donation of electron density from the filled d orbital of metal to the vacant pi star orbital of the carbon monoxide, resulting in the formation of pi bond. This effect is known as synergic effect. So combining these two, we can show the bonding in carbon monoxide is we have this metal, we have this carbon monoxide. Now force these overlaps, giving you sigma bond. After this metal, that is fill the orbital of metal and the vacant pi orbital of ligand again overlaps, giving you the pi bond. So this can be written as metal carbon monoxide. So metal forms a dative bond by accepting pair of electron from carbon monoxide, and this is sigma bond. Simultaneously, metal is back donating electron density from filled d orbital to the vacant pi star orbital of carbon monoxide. This is pi bond, this is sigma bond. So this is how the metal carbonyl complex are stabilized. So from this we can come to the conclusion why metal carbonyls are very stable. The reason is due to this synergic effect. There is a formation of pi bond between metal carbon. That means the metal carbon bond order is 2. So because of this increase in bond order, the bond strength of metal carbon increases. As the bond strength increases, the stability of complex also increases. So the points that we have to keep in mind while discussing the bonding in metal carbonyl is the bonding between metal and carbon. First, both metal and carbon monoxide acts as an acid as well as base. In the formation of sigma bond, ligand is transferring electron density to the vacant hybrid orbital of the central metal. So ligand is acting as a base, metal is acting as an acid. So this formation of sigma bond is with overlap between the vacant hybrid orbital of metal with the filled sigma orbital of carbon monoxide. We have this. Now during the formation of pi bond, metal is transferring the excess accumulated electron density from itself to the vacant antibonding orbital of the carbon monoxide, and this is formed between the filled d orbital of metal and the vacant pi star orbital of carbon monoxide that we have shown here. So this is what we call a synergic effect. Synergic effect is formation of back donation or the pi bond between the metal and the carbon monoxide by transferring electron density from the filled d orbitals to the vacant pi star orbital of carbon monoxide. So this is how metal carbonyls are formed. Now as the strength of metal carbon bond increases, the bond order of carbon oxygen in carbon monoxide will decrease. As the bond order between carbon oxygen decreases, bond length will increase. So this strength of pi bond increases as the tendency for this back donation increases. So tendency for back donation will increase provided electron density on metal is more and more. As electron density on metal increases, back donation tendency will increase. So there are some complex in which the carbonyl, metal carbonyl carries a negative charge. So when this metal carbonyl carries a negative charge, the metal exists in the negative oxidation state. As the metal exists in negative oxidation stage, the electron density on metal is very high. As the electron density is high, the back donation tendency will increase. As the back donation tendency increases, the bond strength between metal and carbon will increase. So when the metal carbon bond strength increases, the bond order of carbon oxygen, that is bond which are supposed to be triple bond, now this is less than triple bond, or bond weakens, or the bond length of carbon oxygen bond increases. This is the formation of metal carbonyl. I hope the point is clear. Now after this metal carbonyl, we'll go to the stability of the complex. Now coming to the stability of complex, now we are having a bond between the metal and ligand. Now this ligand is transferring electrons to the vacant hybrid orbital of the central metal. So due to this, there exists a bond between this metal and ligand. Now this formation of metal ligand complex may be assumed to occur in a number of steps, including the equilibrium. That means the formation of metal ligand bond can be assumed to be an equilibrium process in which addition of ligand takes place in single steps. Means suppose we have a number of ligand which is to be attached to a central metal. So it's not like all ligands are coming and simultaneously bonded to the metal. Ligand attached to the metal atom one by one. So each and every step is assumed to be an equilibrium state. So whenever we have this equilibrium, we can explain this in terms of equilibrium constant. So this equilibrium constant measures the stability of the complex. If the equilibrium constant is more, obviously the reaction moves in the forward direction, the formation of complex will be more stabilized. If the equilibrium constant is less, that means the reaction is more towards the reactant side than towards the product side. If the reaction is more towards the reactant side, then the stability of the complex will be less. So let's start with formation of this complex MLX. Yeah, let this be N, where N is the coordination number. This may be 1, 2, 3, 4, 5, 6, and let this be the charge on this complex. This is coordination number. So as I told you, this formation of metal ligand can be assumed to be an equilibrium step involving stepwise formation. So let's start this. So we have this metal. This metal combines with this ligand. We have an equilibrium, that is ML ligand is formed with certain charges. Now since we have an equilibrium, this can be expressed by equilibrium constant K1, that is individual equilibrium constant. So this is the concentration of Ml divided by the concentration of M into the concentration of N, that is equilibrium constant. Now in the second step, we are starting with this Ml. Now this Ml reacts with second ligand, and this forms the complex Ml2. Second step, let the charges be B. So we have Second step, let this be expressed by K2. So K2 is Ml2 Ml into L. Similarly, we can take in the next step Ml2 combines with L, then we have Ml3. This being the charge, we can have K3, so that is Ml3 C divided by Ml2 into concentration of ligand. So this keeps on doing. In the final step, in the last step, let this be the last step, that is X. When we have looked at this, Ml n minus 1 will combine with L and this gives you MLN X plus minus. So let this be nth step to Kn. Then we have this MLN X plus minus divided by MLN minus 1, because in the last step before this, it should have been ML minus 1. Now this is individual stepwise formation constant. So this constant is also known as formation constant because this results in the formation of complex. Now the net reaction. Net reaction is, look at this metal will combine. This will cancel out. So ultimately total number of L is NL. So this metal combines with N moles of ligand and this results in the formation of complex MLN X plus minus. So this will automatically cancel out. So let this be K total. So K total, equilibrium constant total, this is MLN X plus minus divided by concentration of M into concentration of L raised to the power N. Now the question is, if this K total is more, so K total being large means the concentration or the quantity of this numerator should be large, the quantity of this denominator should be less. If this ratio numerator is more than denominator, then this ratio will be more. So numerator more means the concentration of the complex form will be more. As the concentration of complex is more, the reaction is shifting in forward direction. As the reaction is shifting in forward direction, the stability of the complex will be more. So the stability is defined by this equilibrium constant. So more is the equilibrium constant, more will be the stability. So therefore look at this. More is the value of Kt, more will be the stability of complex. So this Kt is known as stability constant. Though this is an equilibrium constant, so for this Kt, which is the equilibrium constant for the overall formation of this complex between metal and ligand to give it this complex, this is also known as stability constant, or sometimes this is also known as formation constant, also known as formation constant Kf. So this Kf is nothing but the total equilibrium constant for the formation of complex. So the equilibrium constant large means the stability constant is more, complex will be more stable. Kt large means the formation constant. Another name of Kt, that is the formation constant. So if the formation constant is more, the complex should be more stable. Now this total formation constant or equilibrium constant has to be related to this individual equilibrium constant. So the relationship between these two is, if you look at this, Kt, that is the total equilibrium constant, is equals to the product of individual step equilibrium constants. So in a complex formation involving number of individual equilibrium steps, the total or the final or the overall equilibrium constant is equals to the product of the individual step equilibrium constant, or you can say log of this total or equilibrium constant is equals to log K1 plus log K2 plus log Kn. So either we can express in terms of this Kt is equals to the product of individual constant, or the logarithm of the total equilibrium constant is equals to summation of the logarithm of the individual equilibrium constant. So what we are going to discuss is, first thing that you have to keep in mind is, formation of complex is an multi-step involving number of equilibrium steps. The net resultant is the summation of individual equilibrium steps. The final equilibrium constant is equals to the product of individual step equilibrium constant. So for the stabilization of this complex, the net equilibrium constant should be having large value. When the net equilibrium constant or the formation constant is having large value, the reaction is shifting in the forward direction. As the reaction is shifting in the forward direction, there is more tendency for the formation of this complex. The complex will be stabilized. Now, in some of the books, rather than this stability constant, this is sometimes explained in terms of instability constant. Instability constant. So this instability constant is nothing but 1 by K total. So now look at this. If the instability constant is less, that means the stability constant will be more. So this is another way to define the stability. So rather than stability constant, some of the questions may say that the instability constant. So if you are having instability constant, so instability constant is nothing but 1 inverse of the stability constant. If the instability constant is more, that means the value of Kt is less, stability of the complex will be less. If the instability constant is less, that means the value of Kt will be more. If the value of Kt is more, stability of the complex will be more. So look at this. Stability of complex is directly proportional to stability is inversely proportional to 1 by Kt, that is instability constant. This is stability constant. So this is how we define stability of a complex from the equilibrium constant. So for this complex to be stable, equilibrium constant should be large, or the instability constant, that is the inverse of the stability constant, should be having low value. Now there are many factors which decide the stability of the complex. First, the bonding between metal and ligand should be more strong. That is based on the metal. Now look at this. Metal can have more than one oxidation state. As the positive charge, as the oxidation state of metal increases, the polarizing power of metal ion increases, the stability of the complex also increases. So whenever a metal can exist in more than one oxidation state. The higher oxidation state will be forming the stable complex. Second, ligand. Now look at this ligand. We have a spectrochemical series, weak field ligand and strong field ligand. The bond formed between metal and the strong field ligand is always more stable than the bond formed between metal and the weak field ligand. The reason being, we have a strong field ligand. With this strong field ligand, the crystal field stabilization energy will be more. As the crystal field stabilization energy is increased, the stability of the complex also increase. Third, this also depends on the geometry of the complex. Now if you look at this tetrahedral complex and octahedral complex, the crystal field splitting energy in octahedral complex is more than that of tetrahedral complex. So in octahedral complex, splitting energy or stabilization energy is more, so octahedral complex are more stable than the tetrahedral complex. Now again coming to square planar complex, as in the square planar complex, as the splitting is further increases, the crystal field stabilization energy increases, so square planar complex are more stable than the octahedral complex. So stability, overall stability, this factor depends on metal, ligand, crystal field stabilization energy, or this geometry of the complex also. This is what we talk about, the stabilization of the complex. So to measure the stability, mathematically we should have this parameter. Once we have this parameter, that is stability constant or Kt, we can easily define or compare the stabilities of different complex species. But if question says we have with the same ligand the metal in two different oxidation states, the complex formed by metal in the higher oxidation state will always be more stable than the lower oxidation state. For the same metal in the same oxidation state with different ligands, so complex with the strong field ligand will always be more stable than the complex with weak field ligand. Second, when we compare the stability of tetrahedral and octahedral, obviously the crystal field stabilization energy of octahedral complex being more than the tetrahedral complex, octahedral complex will always be more stable than the tetrahedral complex. So this is the factors on which the stability of complex. So factors depends on metal, ligand, coordination number, that is the geometry of the complex, and the crystal field stabilization energy. So with this we come to the end of this chapter, that is the stabilization of complex. So far so we have discussed theories of bonding, how metal ligand bonds are formed in various theorems, tetrahedral complex, octahedral complex, square planar complex. We have taken two different theories, valency bond theory, which is known as VBT, which takes into account the hybridization concept. By use of this, we explain some of the properties, those properties which cannot be explained by valency bond theory, we explain by crystal field theory, which is more advanced than that of the valency bond theory. Then we explain why the metal carbonyl bonds are more stable, much more stable than the stability of the complex. So this is all about the coordination chemistry or the coordination compounds. Thank you all.